Okay. Awesome. Yeah. So we're going to go ahead and get started with, just reviewing the LRU cache. There are a few things that were actually wrong about the starter code that we gave you, and I apologize for the problems with that. But so some of the things that were wrong with the starter code, I just want to briefly mention those first. So actually, to do that, let me just quickly go to the GitHub directly, because I already fixed those issues in my local code right here. So it is the coding challenges, right? Hold on.
CS1.
Yeah, here it is. Oops, wrong one. Okay, so we have LRU cache. Yeah, so just to explain the problems. So first off, you'll notice that we have class list right here, and it has this open brace, and then we don't have a closing brace on line 180. So that needed to be fixed. There needed to be a closing brace here. A few other issues were that delete. So these three methods right here: insert after, insert before, and delete. These were not meant to be inside the list class. This is actually a function of the individual list node in this case. So these three should actually be moved into list node. Okay, so those are three methods that are inside list node. And then finally, one thing that was interesting about this one was that the naming of shift and unshift was actually flipped. So normally, shift will actually remove from the front of the list, and unshift is what's going to actually add to the front of the list. Shift is basically saying, hey, let me get rid of the first element. Unshift is like, hey, okay, let me put a first element back in. You can imagine you're literally just shifting the list down. So that's why you're removing an element there. So I'm not unfortunately I'm not really sure why this code was like that. I apologize for I think it should have just been looked over more. Really sorry about that. That probably just caused a lot of confusion and issues up front. That combined with the fact that this is definitely one of the more challenging coding challenges that we had. It's totally understandable if that tripped you guys up a lot. Also, just generally, the code for this is a little bit tricky, and you do have to think about it. So if you didn't quite get this coding challenge, it's totally understandable. And I think there are some major changes that we're going to be making to it going forward. Yeah, so I just wanted to mention all of that up front. I apologize for why the code was in this state. I'm not sure why it was like that. But yeah, so I went ahead and fixed all of those things in my code. So you can see, I added that closing brace on line, in this case on line 179 for me, I added that closing brace. I moved those three methods, insert after, insert before, and delete, into list node. And then I went ahead and changed the naming of unshift and shift. And I also had to update all of the calls to those with the changed naming. So that will just hopefully make things a little bit easier to understand. That way this matches the array, the naming of the corresponding array methods. Okay, cool. So I'm going to go ahead and get started with it. If you guys have any questions about this, definitely let me know. I'll try to ask a few questions along the way as well. Okay. So great. So we want to create an LRU cache, right? And I'm just going to quickly just go over what is inside, what the description of an LRU cache is. So just to repeat what was said here, the idea is that we have a set of elements that we're storing. Okay, so it's a cache, so it stores some elements. Usually the reason for a cache is you have some expensive operation and you perform that operation, and you don't want to repeatedly perform that operation. So instead you just store the result inside a cache. Okay, and that cache holds the result. So next time you need the result of that operation, instead of repeating it again, you just ask the cache, you're like, hey, cache, give me the result of this operation, so I don't have to repeat the calculation again. It's just a way of storing a pre-computed result of some sort. That's the entire point of a cache. So the LRU cache, okay, is a special type of cache. So generally, when you have caches usually have some size, right? They store a certain number of elements. Because the RAM on your machine, because the memory on your machine is limited, we can't have our caches be unlimited in size. They need to be restricted so they only take up a portion of that RAM. So usually we'll give the cache a max size. We'll say like, hey, this cache can store 100 megabytes, or this cache can store like 5,000 elements. We'll give it some cap like that. And the cache, should not exceed that amount. And so what that means is when we're storing all of these pre-computed values into the cache, what we're going to do is, what we're going to do with that is basically say at some point, if we have too many pre-computed values, right? If some point the number of items that we are storing is actually greater, the size of the items or the number of items is greater than the limit that we have, then we need to get rid of some item, right? So our cache has a restricted size, and we need to get rid of some other item in order to make room for this new item that someone wants to insert into the cache. Okay. So what that means is that we have to have some eviction policy. So it's the idea of we need to figure out what element we actually want to remove. Okay. So the way that the LRU cache works is it picks the element that it wants to remove based off the element that was least recently used. Okay, that's why it's called LRU. So what does least recently used mean? Well, basically, we keep track of when elements were read off of the cache. Okay, so when an element is, we consider an element used when it's actually read or when it's inserted, basically. So when we set the element for the first time, that was when it was used. When we get the element in subsequent iterations, that time, at that point in time, that is when that specific element is used. Okay. And so what we do is we remove the element that was least recently used. So we remove the element with basically the oldest used timestamp. Does that make sense? The one that was used the longest ago, because it doesn't seem like that element is particularly useful. It seems like we're not really accessing that element, hence we want to get rid of it. Does that concept make sense to everyone? I'll go over this code directly, but I wanted to make sure that there was a clarity as to what the LRU cache actually does. Okay, cool. Yeah, if you have any questions about that, definitely feel free to ask, and I'll try to maintain a good, try to maintain a view over Slack. Okay, so let's look at this specific example here. So we have const cache is equal to new LRU cache 3. Okay, 3 is going to be the argument we pass to the constructor. It's the limit of 3 items. And then we have all of these set and get calls. So basically, initially, we're going to insert 3 elements, okay? So these first 3 elements right here, item 1, item 2, and item 3, they're going to be key value pairs. Item 1, item 2, and item 3 are the keys, and the corresponding values are A, B, and C for those 3 items. Up until this point, when we have 3 items, the cache can hold all of them, right? So it has a limit of 3 items. We're storing 3 items. We set all of those, we're good. All 3 of those are stored in the cache. Now it comes up to item 4. Okay, we're going to go ahead and store an item 4. So what happens at this point? Well, because we are trying to add an additional element, and we're already at our limit of 3 elements in this case, we need to remove an element, right? And what we're going to do is remove the element that was least recently used, okay? And in this case, because the least recently used sort of timestamps you can think of is C is the newest because it was inserted the last. B was inserted slightly before, and A was inserted the first. So A is actually the oldest element. Okay, we're doing insertion, not get right now because we never got these elements, right? So whenever you insert the element or whenever you get the element, both of those update the used timestamp. We've only inserted these elements, so basically C is the newest and A is the oldest in terms of insertion. Okay, so when we set item 4 to D, A is the oldest, A is the least recently used, which means we should evict A, okay, or we should evict item 1. Okay, we should evict item 1 that corresponds to A. Okay, so we should evict this key value pair right here because it is the oldest. So hence when we get item 3, that gives us back C. When we get item 2, that gives us back B. Those were set and those are still in the cache. But when we get item 1, of course, we get null because there's no item 1 left. Okay, and like matter now, if we were to set an item 5e, what's going to happen is that when we set up this item 5, we were already at our limit, and so we're going to remove the least recently used item. In this case, we've accessed item 3 and item 2. Okay, we've gotten item 3 and item 2. Okay, So both of their timestamps, okay, both of their like used timestamps, are updated. And so the least recently used item now is actually item 4. Okay, so item 2 is the newest because it was the last operation, the last get or set operation was on item 2. Then the operation before that was on item 3, and then the operation before that was on item 4, right? So item 4 is the oldest item that had any operation applied to it in this case. In this case, the set operation. Okay, so now item 4 is least recently used. We get rid of it and we replace it, and then we add in item 5 corresponding to E. Okay, and then again, if we add item 6, well, now item 3 is the oldest, right? Because item 5, it goes item 5 is the newest, item 2 is the second newest, item 3 is the oldest. Does that make sense, everyone? Any questions about any of that? Okay. All right, I'm going to assume that makes sense. So what we're going to do, okay, so that's the general concept. Let's go ahead and look at what the code that's provided to us. Usually a good idea to look at the code just to get a sense of how this code works. The really important points of this code, so first off, we have this list node, which represents a single list in our linked list. And then we have, we have our list, our entire list class right here, okay? And so for the list class, you'll notice that let me see right here. Yeah, so you'll notice that we have, we have this these two functions. Okay, so first off, we sort of have these 4 functions that let us actually work with the list, right? So we have unshift and shift, which again will let us insert to the front of the list, remove from the front of the list. We have push and pop, which lets us insert at the end of the list and remove from the end of the list, just like you have for arrays. And then we have these 2 methods, move to front and move to end. So these basically take some node that's in the list and then reposition that element at the front of the list, okay, or reposition that element at the end of the list, okay? And it's interesting, like these 2 methods are not usually standard, right? Because if you think about it, like the standard methods that you see in any list or any array in this case is like shift, unshift, push, pop. So seeing move to front and move to end are like these are, seeing these methods should be sort of an indicator that like, hey, like why are these methods here? They might be useful for this specific task, okay? In fact, we are going to use one of them. Okay, so the idea for our code, okay, the idea for our code is that you know how I basically mentioned that each element has like a timestamp where it's least recently used, right? Like the idea of when was the last operation performed on this element. Well, another way of considering that timestamp, another way of representing that timestamp is instead of actually storing a time, what we can do is we can make the order of the list matter. Okay, so basically what we can do is we can say, hey, the element that is the newest in the list, okay, like the newest, the newest element, that's going to be the last element in the list. It's going to be the tail of our linked list, okay? And then the oldest element in the list, the element that should be removed, okay, is going to be the first element, okay? So the first element is the oldest element, and the last element is the newest element, right? And if every time we add an element to the end of the list, okay, then that makes sense, right? Because when we add an element to the end of the list, that element is now like the newest element that had an operation on it. Okay, so we got to be a little careful though. In order to maintain this condition, right? In order to maintain this condition of ordering, what we have to do is each time we retrieve an element, each time we make a get, each time we call get on a specific element, we want to move that element to the end of the list because that element has now just been accessed. Okay, so that would be the element with the newest, that is considered newest, okay? So just to recap, again, like the ordering of our list, we're gonna make the ordering of our list matter here, okay? So the first element in our list, the head of the list is going to be the least recently used element. It's gonna be the oldest element. And the last element is gonna be the newest element. Each time we perform a set operation, we're gonna go ahead and add an element to the end of the list. So that way, because that element was, in fact, the last element that was just added. It's the newest element. Each time we perform a get operation, we're going to move the element that we got to the end of the list. So it's also considered to be the newest element. Okay, so that's how we maintain that condition while we're working with our list. Does that make sense to everyone? That's probably the most important thing of this problem. And that's why we have move to front or move to end, depending on how you want to think about it. Basically, if we're going to move things to the end, we want to have that method, right? That's going to allow us to maintain this condition on our list. Any questions about that? Okay. Yeah, just let me know if you guys have any questions about that. All right, so okay, so let me go ahead and work on this a little bit now. Okay, so basically the idea again, so we want to make sure that we maintain that invariant. So initially, maintain that condition of the ordering of the list. We just have to make sure we're really cognizant of that while we're implementing each one of these methods. So for the constructor, what do we need to do? Well, of course, we need to actually have the list that we're working with, and we need to keep track of the limit alongside the size of the list, right? We eventually want to return the list, and we need to keep track of the size to know when we're supposed to remove things. So we want to keep track of all of that. So we go ahead and set this.limit is equal to limit, basically just keeping track of the limit for further use. We're gonna go ahead and set this.size equal to 0 because initially the list has no elements, the cache has no elements. We're gonna go ahead and initialize a list. So this.list is equal to new list, or new list, right? And of course, the list implementation is down here provided to us, okay? Okay, and that'll be it for now, but we're gonna go and revisit this in a second. Okay, for size, we can just return this.size, okay? As long as we keep this.size updated, returning this.size is gonna work successfully, okay? All right, now let's go ahead and think about get key, okay? So if we want to get a key from this cache, okay, we need to basically find the key within our list, right? We need to find the key within our list, and then we need to return the value that's associated with that key, right? So our list is going to be our cache. It contains our key value pairs, and then we're going to go ahead and we want to find the associated value with this key. Okay, so what you might think about doing is okay, let me loop through our list, right? So go through our list element, node by node or element by element, and find the first node that contains key, right? Then return the corresponding value. So that might be one approach that you think of. Can someone tell me what's wrong about this, or what's wrong about this approach, or what? I mean, this approach is going to work, but why can't we use this approach? Any ideas? Yeah, so Eli mentioned this. It's really the time complexity, remember? So this is based off the instructions. An important part of the instructions is an LRU cache gets O of 1 get key and set key operations, right? So get key needs to be O of 1, which means we can't make get key rely on the number of elements in any way, right? Like it should not take O of n time to perform get key. And right now, if we want to go through our list node by node, well, in the worst case scenario, it's going to take us, we're going to have to loop through every element in our list, or so we're going to have to go through every node in order to find this key. And so that's going to be an O of n operation, right? So we're going to violate this O of 1 constraint that we're given. Okay, so we can't actually go through our list node by node. Like, we're not allowed to do this, okay? So instead, what we need is we need some sort, we basically need a way to immediately find a value associated with this key, okay? So what data structure immediately just gives you the value that's associated with the key? Yeah, so it's an object, right? So just a regular object. If I have an object, so I'm just going to go ahead and create one. I'm going to go ahead and create a storage, okay? And storage is just going to represent, my object that contains the different values in this cache, the different key value pairs, to be precise. So now what I can do is I can just access the value by doing this.storage of key, right? This is an O of 1 operation. This immediately gives me the key. This immediately gives me the value associated with the key, okay? So that's what I need to do in order to match that O of 1 constraint. I need to introduce this storage because I can't loop through the list. Okay, so that being said, the question now is what should the values actually be? Okay, obviously the keys are the keys given to us by the user, but what should the value actually be, the corresponding value to that key? Okay, like maybe you think that the value should be, so maybe you think that the value should be the actual value that corresponds to that key. When we set that key, okay, maybe you want the value to be the corresponding value. Okay, so maybe this dot storage, basically maps in this case item 1 to A, item 2 to B, item 3 to C, etc. Okay, maybe storage just directly holds these. What would be the problem with storage just directly holding these key value pairs, item 1A, item 2B, item 3C? What would be problematic about that? So again, think about the time complexity of get. Okay. Position in the list. What exactly do you mean by that, Alon? Yeah, right, exactly. So you're totally on the right track here. So the idea is that if we store the key value pairs, right, if we store item 1A, the problem is that we still need to update our list, right? Remember that that inside get, what we want to do is whenever we find a specific value associated with that key, we want to take that list node, and we want to move that list node to the end of the list, right? That was the entire point. We want to maintain the condition that, the least recently used element is the first element and the newest element is the last element, right? So in order to maintain that condition, we do need to find the element, we do need to find the node that contains key, okay, in our list, okay? And if our storage were to contain just the key value pairs that the user inputted, like item 1A, for instance, we would still need to go through the entire list. We would still need to go through the entire list to find where item 1 is in the list so that we can take that node and we can move it to the end, right? So if our storage just mapped, again, item 1 to A, which is just the user-defined key to the user-defined value, there would be no way for us to know which node we actually need to move to the end. And because of that, we'd have to loop through the list and find that node. And so hence it would still be an O of N operation. Okay, so what we need, we can't actually associate the key with a direct value. What we really want to do is associate the key with a node. Okay, so we want to associate each key in our storage with the actual list node, okay, in the list. Okay, so basically, if this dot storage of key, okay, so actually, well, here, I'll do this. Const node is equal to this dot storage of key. If there's a node, right, it might be the case that the person gave us an invalid key or a key that doesn't exist. So in that case, we're just going to go ahead and return null, right? I can go ahead and make that explicit by just doing this. So if there's a node, we're going to do something with that node. Otherwise, we're going to return null because we couldn't find that key. Okay, so if there's a node, okay, so what do we do in this case? Well, what we need to do is we need to go ahead and move that node to the end, right? Just like we said before. So basically, we call this.list.move to end node, okay? And then we want to go ahead and return the value, okay? So how do we return the value? Well, the way that we return the value is that it depends on what our nodes actually contain, right? So what is the value that's within each node? We're basically allowed in our list to set the values up, right? Basically, whenever we insert something to our list, whenever we, for instance, push something onto our list, we're pushing some value. We're allowed to decide what this value is, right? This value right here, we're allowed to decide what it is. So inside the node will contain that value. So we can choose, there are various options here, but one thing that we can do is we can go ahead and just make it so that the node's value is in fact the user-defined value that they gave to us, okay? So remember, each list node, so node is a list node object, okay? It's a list node object, a list node that's within the linked list, so it's a list node object. And this has a dot val, right? It has a dot val, which represents the value of this node. And that's like that, that's the value that we give that node when we go ahead and add an element into the list. Okay. And so when we add an element to the list, we're just going to add the corresponding value. So we're going to say, hey, item 1, okay, corresponds to A. Okay. So we're going to go ahead and add A. So we're going to create a new list node when we perform the set, and the value of the list node will just be the string A. Okay. And then in our storage, we'll keep track of, hey, item 1 is associated with this node right here. Does that make sense? So basically, the node.val is going to represent the actual value that this key maps to. Okay, so each list node has a value. We're going to make that value the corresponding value that the user gave us. So the user gave us, item 1A. Inside our storage, we're going to store, inside our storage, we're going to have storage of item 1. That's going to be, that's going to correspond to a list node, and that list node will have a value that has A. Okay, so basically the value. Maybe I'll make this look like an object a little bit more. The list node will basically be an object that has a val of A. Okay? So memory talking. As we refer the node, and the node is a object, we'll have direct access to a memory point instead of storing new data, right? Time complexity O1, memory used, just link memory. Yeah, so exactly. So because the idea is that we have this storage and we're just accessing a key value pair, it's O of 1 to actually access that. And in terms of the memory to store this key value pair, yeah, I mean basically we have to store the key inside the storage, and then we have a reference to the node, and then we have the node object itself. But yeah, that's like a constant amount. You can consider that a constant amount of room per individual item in the list. Okay. All right. So we have that. Now let's go ahead and implement set. Okay, so for set, remember that we basically just want to add the element to the end of the list. Okay, but of course we need to evict if it's too big. So first off, let me just assume that the list isn't too big and let me add the element. Okay, so let's assume that the list can actually fit our element. So what we're going to do is we're going to call this.list.push val. Okay? That's exactly, so basically we're just going to add an element to the end of the list. We're going to add this value right here to the end of the list. Okay, but now we have to associate that key with that value. And how do we do that? Well, that's inside our storage, right? So storage of key is going to be equal to something, right? To something. Like, what do we want right here, right? You might think that I can just put val here, but again, remember, we're assuming, just like I said before, we're assuming that our storage is mapping keys to list nodes. Okay, it's not mapping keys to values, it's mapping keys to list nodes. So what we want is to actually map this key to the node that corresponds to this key. And the node that corresponds to this key is the last node that's in the list. Okay, and the last node that's in the list is the list tail. So that's this.list.tail. Okay? Does that make sense to everyone? So again, we're pushing a new node onto the list. That becomes the new list tail. Okay, that tail has a value, which is val. Okay, the user provided value. And then we're associating the key in our storage with that value. So the key is equal to this.list.tail. Cool, yeah, awesome. Yeah. So this is an example use case of why we would need a reference to the tail, right? This makes it really easy for us to access the tail. Having a doubly linked list makes it easy for us to access the tail, and that's really important to make this operation O of 1. If we had to loop through the entire list to access the tail, well, that would defeat the purpose of O of 1. So the doubly linked list is very useful here. It gives us direct access to the tail, so we don't have to worry about looping through the list. Perfect. So this is the case, again, just to repeat, this is the case when we have space. But we don't always have space, right? We don't always have space. So we need to check that. So if this dot size, okay, is equal, okay, actually before I do that, one last thing I have to do here is I have to, of course, increment our size because we're adding an element to the list, right? So we got to make sure that we do that. So if now what we have to do is at the beginning of set, if this dot size is equal to this dot limit. So if we've already reached our limit, okay, what this means now is, hey, the problem right now is that we need to go ahead and evict an element. We cannot store more than limit elements, okay? We've hit our limit, hence we need to evict an element before we add the current element in, okay? So now we have to go ahead and remove a node from our list. Okay, can someone tell me how, like, which node would I remove from the list? Yep, exactly. So Alon and Eli both say the head node. That's exactly right, right? Remember, we maintained that one condition, okay? When we maintain a condition throughout a data structure, or throughout any piece of code, we usually call that an invariant. It's basically a condition that does not vary. It's a condition that always holds. So you might see me use this word invariant. Invariant means a condition that always holds. Okay, so our invariant for our entire list, for our entire LRU cache right here, was that our list is in the order from oldest to newest, from least used to most recently used, like least recently used to most recently used. Okay, so that's why in order to basically remove in order to like figure out which element to remove, we just remove the head of our list. It's that easy because we maintain that invariant, right? The newest node is always at the end, or the node that has the latest operation on it is always at the end. The oldest node is always at the beginning. Okay, because we maintain that invariant, all we need to do is get rid of the first element. Okay, so basically the way that we need to get rid of the first element is we can just do this dot list, right? In this case, shift, right? Remember, shift, just to repeat, removes the first element from the list. Okay, there's a direct method for that. So we're gonna go ahead and just call this dot list dot shift to get rid of that element. Okay. Now the next thing that we have to do is we have to make sure our size doesn't get incremented, right? So after calling list.shift, all of this code will be executed, but the size is now going to increment above limit. We really don't want that. So in order to counter this, we're just going to go ahead and drop the size by 1. Basically, we just removed an element, so we're going to reduce the size by 1 because we removed that element, and then we're immediately going to add a new element in, so the size is going to go back up to the limit. Okay, so we have to make sure to reduce our size by 1. Is there an ordering algorithm or something we can call this operation of put the last to the first? Well, it's not. I wouldn't say it's necessarily an algorithm per se. It's just the idea that every time every time we work with a list node, every time anyone performs a get or set operation on a list node, we make sure that that list node gets moved or gets added to the end of the list. So it's not, there's not like a clear, like, I guess that is really the algorithm. The algorithm is simply when an operation gets performed on a list element, make sure that that list element is at the end of the list. So that's sort of the algorithm there. It's not an infinite loop again. Yeah, exactly. Yeah. That's just how it works. It's not an infinite loop because we're just making sure that that element is at the end, right? We're not looping in any way. We're just saying, hey, push this element, like move this element to the end. That's it. Okay, cool. So there's one more thing I need to do here. What is the last thing I need to do? I'm removing an element from the list. What does that mean about our data structures? Is there anything that I need to adjust with respect to the data that's in this LRU cache? Right. So the idea here is that, remember, we're removing something, and we also keep track of the keys inside of our storage. Right? We keep track of all of the keys inside of our storage. So we need to basically get rid, okay? We need to get rid of the corresponding storage element, right? Because that whatever key corresponded to this node, that key is no longer in the cache, right? We've evicted it from the cache. So we need to update our storage and remove that element from the storage. Okay, now this is the hard part, right? Like basically, what do we delete from this dot storage? Right? Like we want to basically delete delete this dot storage, and we want to pass in some key here, right? We want to remove some key from this dot storage, right? So this is the syntax for it, delete, to delete a key from an object. This dot storage is our object, and we want to specify the key here. The problem is we don't know what key it is. Okay, we can access the element, we can access the node that is about to be removed. That's the head element right here. But the value of the head element, this.list.head.val, this is a value, it's not a key, right? It's a value. So we don't know what the corresponding key actually was. We only ever stored in our list, we only ever stored the values, right? We only stored the values. Does that make sense? So there's no way for us to know what key corresponded to this node. There is one way, which is that we could go through our entire storage, okay, and figure out which key maps to the head node, right? We could go through the entire storage, basically go through every value inside our storage object and check if that value is equal to the head node. And if it is, then we know that that key is the one we need to remove. Okay, but what's the problem with that? What's the problem with me potentially looping through my storage and trying to find which one is the head node? Yeah, again, it's the O of 1 issue, right? Just like Patrick said, it's the O of 1 issue. We need to make sure it's O of 1, and storage contains all the elements, hence it's going to be O of n, so we can't do that. Okay, so basically what this means is that we need to somehow encode, we don't have to just encode the value in each list element, we have to encode both the value and the key, and that's really the key. Okay, well, I guess that's kind of funny, but yes, we have to have both the key and the value for inside each list node. So instead of pushing just the value, we're going to push both the key and the value. Okay, and that makes us basically, that lets us be able to do this.list.head.val.key. Okay, and this is now going to be the key that we have to remove. Okay, now this is a pretty complicated little access right here, but let me just explain. This.list is the list, right? Head is the first element in the list. It's the first list node. Val is the value of that list node. Each value in our list nodes is an object. It's an object that contains a key and a value. Okay, so hence we need to access the key. Okay, and we have to delete this dot storage of that key. So we're getting rid of the corresponding storage element right here. We're then removing the head element from our list by calling shift. Okay, and then we're going to go ahead and decrement the size. Then we're going to push that key value pair into another list node. This dot storage of key will correspond to this dot list dot tail, right? We're basically going to associate the key with the node, and then we're going to increment our size. Because we changed what the values look like, we also have to modify our get. Right here, when we access the value, it should actually be .val. Okay, so again, it's kind of confusing. Node.val corresponds to the value associated with a list node. And the list node values are these objects right here that have two keys, key and val. So node.val.val represents the object, represents the actual value associated with the key. Does that make sense to everyone? Yeah, it's kind of confusing. Again, node.val, whenever you see node.val, what that means is the value of the node. And we specify the values of the node when we call push, right? And the value of each node is, in this case, an object that also has a val attribute. Hence, node.val.val is going to be the correct value, okay? It's going to be the actual value. It's kind of confusing, but that is how it works. As we add the values, the storage will not be ordered as the list, right? So we don't really care about the ordering of the storage, right? The storage can be ordered however it likes. The main point is that when we get to the limit, we always delete the first element in the list. We always delete the head of the list. So it doesn't matter how storage is ordered. Storage is an object anyway, so the ordering is sort of unclear. Like objects don't have a clear ordering. Arrays do have a clear ordering. So hence we don't really have to worry about the storage ordering. But if we keep ordering storage to the list, we can't just remove the head. So again, the problem here is that objects don't have a clear ordering. It's not clear what the first element of an object actually is. Okay, it's actually different depending on different JavaScript implementations what the first element of an object actually is. Okay, so hence we cannot rely on the ordering of our object at all. We can't say what is the first element in this object. Like that doesn't make any sense. So hence that's why this dot storage, this dot storage is just a mapping from keys to values. It doesn't have any ordering associated with it. This dot list has that ordering, and that's what we're using in order to delete an element. Okay, cool. So let's go ahead. I'm just going to go ahead and run my test. So I basically created some tests right here. Okay, I wrote some tests. Basically, I just directly wrote this code right here out for the most part, and then I just wrote simple assertions. So like, for instance, it says, get item 3, and then there's a comment right here, C. So I basically did exactly that. I was like cache.get item 3, and if item 3 is not equal to C, throw an error. Okay, so I basically wrote a very simple test right here. I could have written an actual test using Mocha or something, but this is a simple way in case you don't want to install Mocha and get all that set up. This is just a really easy way to go ahead and write a test, right? I copy pasted the code. I added in some errors. I added in some throw new errors. Every single time, it didn't actually meet a condition here. So, item 3 should be C, item 2 should be B, item 1 should be null because it's removed, et cetera, et cetera. Okay, does that make sense? So I just basically copy pasted that into a test. So what I can do is, where am I at? LRU cache, so this is gonna be, let me just quickly cd into that. Okay, and then if I go ahead and run that, perfect, okay, actually, wow, so there we go. Okay, so no test.js just worked on the first time. There are no actual errors. So this implementation works based off those tests. However, there is, an issue with this implementation. Okay, so there is an issue. I believe there is an issue with this implementation. So can someone tell me? Okay, think about an edge case. So I'm going to go ahead and set key value pairs in my LRU cache. Okay, can someone think about an edge case? What would be an edge case that I should make sure to test when I'm setting key value pairs? Like what are some combination of key value pairs that might trigger some edge case in my code? Boom. Okay, perfect. Yeah, Julian, that's great. So if you set two keys to be the same, that's exactly right. So let's say that I have my cache, okay, and my cache stores like 3 elements. So I'm just gonna go ahead and repeat this right here. So my cache stores like item A, item 1A, item 2B, item 3C, okay? And now I add in what I do is I add in another item 2, okay? So basically instead of setting item 4, I set item 2, okay? So this is what I'm gonna do instead. I'm gonna set item 2 to D. What happens at this point? Okay, well, if we follow our code, we're going to have 3 elements in our array, right? After these 3 lines, we're going to have 3 elements in our list, right? And then we're going to go ahead and try to set item 2. Let's look at what happens when we set. Well, when we set, we'll notice that the size is equal to the limit, okay, which means that we have to evict something. And then we're going to delete something. We're going to go ahead and evict the first element. The first element is going to be A. Okay, the first element is going to be A. So we get rid of A, and then we go ahead and add in item 2D. Okay, we go ahead and add in item 2D. Now here's the problem. That means that item 2 is located twice in the list. Item 2B is the first element in the list. Item 3C is the second element, and then item 2D is the third element. Okay, that's the key right here. Notice how now, after I process this line, we'll have 3 elements, and 2 of them will have the exact same key. Okay, and that is a huge issue because basically now the question is, what is the real value of item 2, right? Is it item 2B or is it item 2D? Like we don't know what the real value is anymore because there are 2 of them in here, okay? So that's just the wrong behavior completely, right? What the correct behavior is, okay, is that we should go in, we should find the node associated with item 2, okay? And then reset its value, right? If item 2 already exists, we want to update its value. We don't want to remove some other node. We just want to update its value so that there's only one source of truth. There's only one element that has a key, in this case, one node that has a key of item 2. Okay, we don't want 2 of them in there. That's just confusing. We don't know what's actually in the list, okay, or what's actually in our cache. Okay, so what does that mean? So basically what we need to do is we need to check whether this key is actually already inside the list. So basically, we can do that. We've already done that in get for the most part, right? So let's go ahead and try to do that. Const node is equal to this.storage of key. Okay. Actually, before I do this, let's just go ahead and try to update our test cases to make sure that we fail. Okay. So I'm going to go ahead and comment that out. It's usually good when you come up with an edge case. Go ahead and just make sure that you can write a test where your code actually fails. Okay. And if you can do that, that means that you did in fact catch an edge case. Now go fix it. So I'm going to go ahead and do exactly what I said. I'm going to set item 2 to D. Okay. And now how can I actually exercise this error? Well, let me see. Let me think about that. How can I exercise this error? Okay. The way I can exercise this error is I can go ahead and try to get item 1. Right? I still want, so item 1, I should still be able to get item 1, right? Because basically item 1 should still be inside my list. I have not actually added a new key value pair. I'm updating a key value pair so that the value is D. So I should be able to get item 1. So basically if item 1, okay, is, in this case, is not equal to A, okay, throw new error, expected item 1 to be A, but got item 1. Okay, does that make sense? So I'm basically just getting item 1, and I'm making sure that it's still A. Okay, if it's not A, I'm going to go ahead and throw an error. So let's go ahead and try that. All right, excellent. Throw new error. Okay, so basically error expected item 1 to be A, but got null. That's exactly what we expected, right? We perfectly expected that item 1 would be removed incorrectly. So now that our test has failed, let's go ahead and fix this, right? We can reproduce this case. Let's go ahead and fix it and make sure that we actually successfully fix it. Okay, so again, we have to make sure that it actually exists. So const node is equal to this dot storage of key. Okay, and if, okay, so if the node actually exists, that means that it's already inside the array. It's already, already inside the list. Okay, this key already has a designated element inside the list. Okay, so what do we want to do now? Okay, and in fact, what we really want to do, it's pretty simple here. We want to do two things, which is want to update the value. Okay, so we're going to set node.val is equal to val. Okay, so just like we return node.val.val, we got to set node.val.val equal to val here. Again, node.val is this object right here. So .val.val is the actual value, which we're setting equal to val. And then, because again, we're setting this element right now, that was the latest operation, we have to move this node to the end, again, to maintain that same invariant. So this.list.move to end node. Then we're gonna go ahead and return. We're gonna return because there's nothing else we need to do. We don't need to update the size. We don't need to delete anything, nothing like that. We just updated that specific node with the new value. And we moved that node to the end to maintain our invariant. Any questions about that? Let me go ahead and retry that. Boom. Okay, so now nothing goes wrong when I run node test.js. Let me go ahead. Okay, so ideally I would have added this test sort of in addition to all of these tests, but I modified my previous code. So I'm just gonna comment out what I did and then re-comment in the rest of the tests just to make sure they all pass. Ideally, I would have incorporated this into these tests so that the rest of these tests still work exactly as they do. But because I sort of modified this initial code, I have to comment this out right now. But node test.js. Okay, perfect. So all the other tests still work as well. Okay, so that's a great way to basically think about your process here. What you want to be doing is, if you can write a test case that shows that your code fails, you reproduce that. You can reproduce that error. You fix your code. You make sure that error works you make sure that your code now works in that edge case by rerunning your test and making sure your tests pass. And then you want to make sure that the rest of your tests also pass, right? Like you don't just want to solve that error. You want to make sure that everything still works. And that's exactly what I did at the end right there. Does this implementation make sense to everyone? Does anyone have any questions about this? Again, I just want to recap. Pretty difficult implementation, honestly. It definitely takes a lot of time to think about this. There are subtle edge cases that may work even when you look at sort of the code that's given to you, but that you still need to handle, that you need to think about and handle here. So don't worry too much if you didn't, if you weren't able to finish this during the time. But I really hope that based off my description today, you were able to understand it. So please, don't hesitate to ask any questions about it. Right now, I'm going to go ahead and keep this code over here. Are there any other questions I can help answer? And I know we ran over with this coding challenge. I just wanted to make sure that I spent enough time on it though, because it's definitely one of the harder ones. Yeah, I'll be posting all the code. I'll put all the code directly in here, and this is being recorded. So I'll go ahead and post this recording as well, so you have access to that. Oh, the test, yeah, that's a great point. I'll go ahead and add all the tests as well. Any other questions before we wrap it up? You mean like, will we fix all the issues and stuff? Yeah, we're definitely going to do that. Get updated on GitHub. I'm not 100% sure whether we'll update that one directly, just because there might be some like merge conflicts and things that you guys have to deal with, which will be kind of difficult. But we will make sure to update that for like the other classes and everything like that. If you do want, um, if you do want the new updated starter code, I'll find a way to get you that. Maybe I'll just post that directly inside the chat here, so you can get the updated starter code. Okay, cool. Yeah, Alon, sorry for the delay on that. I'll try to look at that. I think I'll be able to get to that today. Yeah. Thanks. Great explanation. Cool. Yep. Awesome. That sounds good, guys. Well, I'm going to go ahead and call it for now. If you have any further questions, please don't hesitate to keep asking. But yeah, that sounds good. And I'm going to go ahead and stop this share right here.